Good evening. We'll wait a minute more and get started. Hope you can hear me and see my screen clearly. If not, please drop a message on chat. Okay, let's get started. So, welcome to the week 5 live session for the GPU architectures and programming course. So, we'll first start with a few of the doubts that were asked last week. Again, I think there were very few of them. So, let's just go through them quickly and then we'll move to the recap for this week. So, one question I got was what is the difference between OpenACC and OpenCL? So again, if you don't know this, if you've never heard of OpenCL at this point, it's fine. We were talking about CUDA and alternatives to CUDA in one of the lectures, right? That's where OpenCL came up. But I think there's dedicated content for OpenCL in week 11 or 12. So you can wait till then to understand more about it. But in general, both are frameworks for heterogeneous programming, meaning you can have CPUs, you can have GPUs. Some of these may also support other custom accelerators. But the main difference between OpenACC and OpenCL is the way they handle parallelism. So if you've used languages like frameworks like OpenMP, you may have noticed some of these compiler directives, right? Saying hash, pragma, parallel. You're basically telling it that this code has to be parallelized in this fashion. So OpenACC is kind of in that way. It uses a lot of these compiler directives or hints for inferring parallelism. It does not explicitly write it out. As in, the programmer doesn't have to do that. The onus is on the compiler. OpenCL has a lot of APIs where you can explicitly control parallelism. That's the main difference. And again, I think popularity wise, OpenCL finds a lot more use as compared to OpenACC. But I'm not sure if OpenACC is in your syllabus at all. So even if you don't know this, it's okay. Since someone asked, I thought I'd spend a couple of minutes on this. Okay, with that, we'll move to the next one. Yeah, this we briefly spoke about it in one of the previous lectures also, but since this week is about warps and warp divergence, I thought I would like briefly go over it again. So the question was, are branch predictors used in GPUs? So my answer was no, they're not. So let's talk a little bit about why that is. So first of all, what happens when there is code with a branch? You've seen that in this week's lectures, right? You basically saw what happens when a warp diverges, how is that handled, and all those masks and flips, which we'll go through in a little bit. But you've seen that. But that being said, GPUs are primarily intended not really to handle branching, right? Unlike CPUs. Additionally, even if there is this sort of branching, right? So in a CPU, what you're trying to do using a branch predictor is basically speculative execution. You're trying to predict ahead of time which fork of the branch will be taken and then fetch those instructions. Again, if you remember from our very first lecture, why are we trying to do that? We are trying to kind of avoid a stall for the CPU, right? Instead of it being idle, you can do all of this ahead of time and eliminate that much time, right? But in case of a GPU, if you think about it, do you really need speculative execution? You don't, because again, you have this notion of massive parallelism, right? So you have the warp scheduler and you have all of these threads that can be instantly switched in and switched out. So if you have an instruction that is taking time, what the scheduler can simply decide to do is switch out that warp and switch in another warp, right? So you don't really need to speculate or know ahead of time which branch is going to execute. Again, so GPUs in a broad sense are intended for the high throughput use case rather than for the low latency use case. So that's the long answer to it. Why branch predictors are still not there in GPUs. One part of the answer is GPUs are not intended for applications where there is a lot of branching. Second thing is you don't need speculative execution as a feature because you can simply switch to something else. So yeah, hope this is also clear. Again, you don't need to know this from the syllabus point of view. It's just something that you would be interested in if you're looking at an architecture perspective, right? I'm sure many of you have learned CPU architecture and now you're learning about GPU architecture. So this is a good question to ask and something to think about. So that's kind of why I've put that in. So I think that is all I had on questions. So before we move to the recap, any other questions from week 1 to week 4 that are still not clear for you, please ask. Discussion forum, I think I took a quick look. There was nothing else this week other than again some doubts in the assignments, which I think the TAs related to that have responded, right? So any other questions? Anything that's not addressed, not clear? I'll just wait for 30 seconds to see if any of you have questions. If not, we'll move to the recap part. Okay, if you don't have questions, let's move to this week 5 content. And again, if you have doubts on any of these, I may not be doing a detailed recap, right? I'll probably cover some concepts in the recap for this. But if you don't understand some of it, again, feel free to drop a message. We can either do it in this week itself or take it up in the next week. So broadly we are looking at warp scheduling and divergence. So you start off by understanding what is a warp, how is that mapped to hardware, how would you map it if you have some resource constraints in terms of SMs and SPs available on a GPU. You also look at the scheduler that's available on the GPU, and understand how this warp scheduling is done and how do you efficiently use thread blocks. And then we come to the branching part of it. So if there is a divergence in control flow, if there is nested branching, how is that actually handled by the GPU? So those are what you've learnt in week 5. Let's start with a quick recap. So again, basic concepts. So you have SM, SP, block and thread. Again, the block and the thread part, I'm sure most of you are clear by now because we've been looking at the launch parameters, right? So we've basically been looking at it from the code perspective. If a developer were to write a kernel, then those parameters are defined in the launch configuration. Now coming to how does this get mapped to hardware, right? That's what you're trying to understand in this week. So you have SMs and SPs on a GPU, and you have this notion of grids and blocks and threads, right, at a software level. So how is this going to map to the hardware? That's basically the core aspect of parallelism, right? How do you take these software constructs and map them into hardware? Just the way, I think we spoke about this levels of abstraction in one of the earlier classes, right? So if you think from the CPU perspective, you have this notion of cores, right? And from a hardware perspective, from a software perspective, you could have processes, you could have threads. Now how this is mapped to those cores, we don't actually study in a lot of detail in the CPU perspective. Again, we are aware that there's a scheduler. You would have heard of context switching. You would have heard that, okay, it may be run on one core, it may shift to another core, things like that, right? So we are trying to kind of get an equivalent understanding in the GPU side of things. So here are some broad rules. So one block cannot be partitioned across multiple SMs. You can only have it in one SM. Then one SM, although the other way is not necessarily true, right? So you could have multiple blocks in one SM. And so here's an example. If there is, again, some of these constraints come in from a hardware perspective, so they may change from one architecture to another. So here we are given an example constraint that an SM can store a maximum of 1024 thread context and the block size is 256. Then we end up with 4 blocks per SM, and we look at some more of these constraints in today's problems. Now coming to the hardware scheduler, this decides which threads to map to a collection of SPs. And again, this is called the SIMT model of execution, which we went through, I think, in week 2 or 3. So this collection of threads is guaranteed to execute in parallel in lockstep. Basically, they all execute together. So this is called a warp. Again, now things like warp size also, you can assume the standard value that is taught in class if it's not mentioned in the question. Otherwise, the question will explicitly mention the warp size is so and so. So for all of these things, have the default value in mind, but read the question carefully to see if a different value is specified to you. For instance, a question may specify that warp size is 32 and you may be using 16 mistakenly. So pay attention to these things when you're solving questions. But the logical notion of a warp is it's a collection of threads that executes in parallel. Now, here we are trying to see how do you efficiently use thread blocks. So now you have some constraints on the target system. So you can have a maximum of 512 threads per block and 1024 threads per SM. And you have a few configurations, right? So in the first one, your block size is 8 cross 8, or your threads per block is 64. The second one, you have 16 cross 16 and your threads per block is 256. The third one, you have 32 cross 32, resulting in a total 1024. So in the third case, or as soon as you see this 1024, you know that it exceeds one of the constraints, which is the 512 threads per block. So this is not a valid configuration. When you have 256, for instance, you could have 4 blocks in the SM, and that would use up the full limit or full capacity that the SM has. So this is a good utilization of the SM and a good configuration of your thread blocks. Whereas in the first example, you have 12 blocks per SM, and this 12 into 64 is still much less than the constraint that is there from the hardware. So you're kind of not utilizing your execution resources fully. Now remember again that all of this is very fine grained, right? So CUDA gives you this fine grained control. So if you want to specify the launch configuration in a certain way, you will be able to do it, and that has direct implications on how fast your program will run, because you may or may not be using the resources effectively. But in today's context, a lot of you may be using GPUs for deep learning, right? So when you do that, these deep learning frameworks, for instance PyTorch or TensorFlow, do this automatically for you. So you don't actually see all of these kernel calls and these launch configurations, but the optimizing these are definitely what gives you performance, right? So for those of you who handwrite CUDA, knowing all these details is very important. If you're working at a framework level or at an even higher level, this is just curiosity for you. This is kind of understanding what happens behind those frameworks. Okay, and then we move on to control flow divergence. So we understood that within a warp, all threads execute the same instruction. So they're basically happening together, right? Typically this is said to be in lockstep. So what happens if you have a branch, if you have an if statement? So you cannot run both the if and else blocks at the same time. This is basically because of the GPU architecture design. It's by design intended that way. So what you will need to do is you will have to first execute one fork and then the other fork. Basically whatever threads fall under this and then whatever threads fall under the other part. But you can understand that this will have a direct consequence on performance. Basically because now you're executing lesser threads than you possibly can, you're breaking the parallelism, right? All 32 or whatever the warp size is not running in parallel. You're going to execute some of them, then the others. So that would cause a performance hit. That is unavoidable. And again, why is this acceptable? Why are people not trying to optimize this? Is because GPUs are not, by design, GPUs are not intended to work with a lot of complex branching code. There is some support, but it is not performant. So yeah. So how do you do this? Again, you have this mask bits, right, which tell you about which threads should execute in that particular branch, and you have this notion of a stack, which is kind of very helpful when you're dealing with nested branches. Here, for instance, you have only 2 possible branches, right? So you don't really need the nesting aspect of it. But basically these mask bits tell you which threads have to execute this. And once that finishes executing, you basically complement all the bits. You flip them so that the other branch, the threads that are needed for the other branch, execute. For instance, here it's a simple even odd check. So in the first time, one set of threads will execute and the other half will execute in the other branch. Yeah, so that's about the recap. I think we have a slightly longer set of questions for today, maybe 12 or 13. So we'll maybe get started with that as soon as we can. But before we go to that, any other questions or doubts in week 5? Please post your message on chat. Since there are a lot of people, I typically disable the mic and video. It gets very distracting. Option 1, which says 12 blocks per SM, is violating one of the constraints. Okay, I'm assuming you're referring to this. Okay, blocks per SM is 12. Yeah, this one explicitly says 8 blocks per SM, so I think so. So, for instance, if this had just said blocks rather than blocks per SM, I would have said it need not have violated it, because the scheduler would have taken care of things such that you execute a few blocks and then in the next batch you execute a few more blocks and so on. But since this says blocks per SM and there is a constraint of 8 blocks per SM, yes, I think that would also violate it, which is something this does not capture. But yeah, if this is a constraint, then this also would be a violation. Any other questions? Okay, if not, we'll get started with the problems. We'll do 5 or 6 of them and then take a 5-minute break. Consider the following grid and block dimensions for a kernel. Grid dimension equal to 4, 2. Block dimension is 4, 4. For a hypothetical GPU architecture, number of SMs is 4, number of SPs per SM is 32. How many thread blocks of the kernel are mapped to a single SM? You can take a couple of minutes and then we'll discuss. Okay, we have one answer saying 8. Okay. We have one more answer. Oh, B. Okay. B is 2. Okay. 2. B. Okay. We'll wait a few more seconds in case some of you are solving. Okay, let's take a look at the answer for this. So it is B2. So let's quickly look at how that is, right? So, so the kernel is launched with 16 threads per block, basically this 4 into 4. And your target GPU has 32 SPs per SM. So your question is asking about a single SM, by the way. So we have to look at only this part. So how many thread blocks can you launch or can you schedule per SM is the question. So you have 16 threads per block and you have 32 SPs. So you can launch a total of 32 by 16, which is 2 blocks per SM. So your answer is B, which is 2. Any doubts here? Okay, if not, we'll move to the next one. In question 1, after deriving the number of thread blocks that can be scheduled to a single SM, how many batches of thread block to SM dispatch would be required to complete the kernel? I can go back, here are your options, so I can go back to the previous question in case you need those numbers. I will go back and you can tell me when you have the answer. Okay, there's one answer saying A. A is 1. So your options are 1, 2, 4, 8. A, okay. We'll wait another minute. So here are the details of the kernel, 4, 2 and 4, 4. Number of SMs is 4, SPs per SM is 32. So now this question is asking you how many batches of thread block to SM dispatch would be needed. Any other answers? Anything that's confusing in the question? So if these questions seem a little difficult to you, I think what all of them need you to clearly understand is this terminology, right? SPs, SMs, your SPs per SM. Similarly, this notion of grids, blocks, threads. You shouldn't get confused by terminology, right? For instance, threads per block versus thread blocks. So try to make a list of these terms that you find in every question and try to understand clearly what each of these mean. Once you get that, I think most of these questions are very, very basic. You will be able to answer them easily. If you get confused about what those terms mean, then it gets harder. But let's look at the answer and then maybe it will be clearer. So how many batches? The answer is A or 1. So how can you get this? So as we saw in the previous question, so how many thread blocks can you launch per SM? We already calculated that. 2 thread blocks. Now how many thread blocks are there for this kernel? You have 4 into 2, 8 blocks. And you have 4 SMs, right? So per SM you can launch 2 blocks. Across 4 SMs you can launch 8 blocks. And your kernel itself has only 8 blocks. So the total number of batches that you would need to dispatch is just 1. The very first time you dispatch to all 4 SMs, you basically accounted for all the blocks that are there in the kernel definition. Another way to do this calculation is in terms of threads, right? So you have 32 SPs per SM and 4 SMs. So in total you can launch 128 threads at a time. Total number of threads that you need for this kernel is what you get by multiplying all four of these together. So that's 8 into 16, which again comes out to be 128. So both of these, the number of threads that you launch in one shot and the total number of threads that you launch for this kernel, both are equal, and therefore one batch of dispatch, or one shot you can basically run all of these threads in this GPU. That's what the question is asking. Is this clearer now? I'll pause here for a few seconds. Please go through the explanation. I think very few of you answered this, so please go through it and let me know if you have any questions. And then we'll move to the next one. Would number of batches be 2 if we have 3 SMs with 32? We actually have variants of these questions. So I think your question will get answered once we solve some of those variants. So we'll hold on to that and then come back to your question. Okay, if there are no other questions, like I said, we'll consider some of these variants to this question. Yeah, so consider that the hypothetical GPU architecture now supports 2 SMs and 16 SPs per SM. For this new GPU architecture and the same kernel launch parameters, how many thread blocks would get mapped to the same SM? So again, quick recap, the kernel launch parameters are 4, 2 and 4, 4. We have one answer saying A. We have one more answer saying C. Okay. Anyone else? Okay, let's take a look at the answer then. So the answer is A, 1. So now the question is, how many thread blocks would get mapped to the SM, right? That's your question. The only change is now that you have 16 SPs per SM. And remember from your previous, the launch configuration, that you have 16 threads per block. But earlier you had 32 SPs, so you did 32 by 16, and therefore 2 blocks could be scheduled. Now you have only 16 SPs, so it's a change in hardware configuration. So therefore you can do only 16 by 16 or 1 block per SM, and therefore your answer is 1. So again, read the question carefully. In this question, the question is how many blocks would get mapped per SM. So all of these things matter, right? If you calculate number of blocks across all SMs, you're going to get something else. If you calculate something else, how many batches are going to get dispatched, it would be something else. So pay attention to what exactly the question is asking. So now we'll go back to the variant that was asked in chat. So would the number of batches be 2 if we have 3 SMs with 32 SPs per SM? So in the variant here, I think we had, so we have 8 blocks, right? And as per the question asked in chat, we have 3 SMs. You can do 2 blocks per SM. So across 3 SMs, you can do 6 blocks. So you'll still have 2 blocks left over, which will have to run in a second batch. So the number of batches would be 2. That is correct. Is that clear now? Sure. 2 people who did not answer question 3, is this clear now? Does this help you understand? Or is something very confusing? If it is, feel free to say that, right? We can spend some time explaining these things in the next week. Again, if you're not able to answer something and you don't ask, I have no way of understanding why you're not able to answer it. So I will not be able to help you address that particular thing. If you let me know, like I think today also we might have 10-15 minutes at the end. So in every session I have that margin, right? So that you can ask questions and we can clarify those doubts. So these questions again are very similar to what is asked in your assignment and what is asked in your exam. So if you're having trouble answering these questions, please use this opportunity to get your doubts clarified. You're not getting it. Okay. Which part is not clear? So was question 1 a little easier? Question 1 and 2, were they a little easier? Okay. So question 2. Okay, so let's go back there, right? So here what is being asked? So let's again maybe start with this part, right? So hopefully question 1 was clear for everyone, or is there any doubts in question 1? Question 1 was clear. Okay, anybody who has doubts in question 1? Okay, I'm assuming not. So let's move to question 2, right? So here we have established that you can kind of fit 2 blocks into 1 SM. Now the question says that you have 4 SMs, right? So let's see pictorially. Something that I find is helpful is to kind of draw this, right? So let's say we have 4 SMs. This is your 1, 2, 3 and 4, right? Now how many blocks do you have in total? From the question, you have 4 into 2, or you have 8 blocks. And what we have already established in question 1 is that you can fit 2 of them per SM, right? What this question is asking you is how many batches do you need to dispatch. So in one batch, what happens? The first 2 blocks get mapped to SM1, the next 2 blocks get mapped to SM2, the next 2 to SM3, and the next 2 to SM4. So in all, you've already mapped 8 blocks to the 4 SMs. So basically whatever your kernel launch specified, you've already completed that. So you basically need to dispatch it only once, or there is only one batch. Now let's say your question had 16 batches, right? And you can still accommodate only 2 per SM. So what you would do in this first batch, you would cover 8 of them, and then once these are complete, you would go ahead and map the 8 to 15 that are left from this 16. So in that case, if there were 16 blocks as part of the kernel launch configuration, how many batches would it take? The first batch would deal with the first 8 of them, and the next batch would deal with the next 8. So overall you have 2 batches, and then the answer would be 2. But in this case, since you have 8 blocks and you can accommodate all of them in one shot, so this is basically like you're executing them in parallel. Think of these as rooms, right? If each room can accommodate 2 people and you had 8 people, how many batches would it take? Think of a movie theater. So if you had just 8 people and you can accommodate 2 per room, which is very small again, but just an example, you can basically accommodate all 8 of them in a single batch. But let's say you had 32 people, and at a time I can only accommodate 8 people. So I'll basically need to do 4 batches of people, right? That's what the question is asking. So once you get this terminology clear, it's again very simple. Again, if drawing it out like this pictorially helps you, please do that. But what is being asked is across all SMs, you can fill so many, which is you can directly get from the previous question. Basically, you can accommodate, in our example, you can accommodate 2 people per room, and you have 4 rooms. So you can accommodate 8 people at a time or in one batch. So you are being asked how long or how many batches does it take to finish all the work that you have, or to accommodate all the people that you have. So in this question, the answer is 1. But if your blocks were different, this would change. Is this clear now? Any other questions? Sure. Again, some of these can be a bit abstract, right? So try to draw it out or try to give yourself an example. That way you'll be able to understand it better. Okay, let's go back to question 3 now and see if it makes sense. So now what changes in question 3? The kernel remains the same. But now your GPU architecture supports 2 SMs and 16 SPs per SM. So again, I'll go back to our simple example so that you get clarity. So now you have 2 rooms and 16 people per room, right? And you have the same launch parameters, meaning how many people do you have or how many blocks do you have? You have 8 at a time, right? So you have 8 in total, but remember that the question here is different. How many blocks would get mapped to a single SM, right? So basically, how many people can you accommodate in a single room? And you have, so going to the answer, now you have 16 people per room. So this is basically your SPs per SM, right? And how many can you accommodate in one shot? It's just 1. That's your block definition. So you can accommodate just 1 instead of 2 the last time, because back then the capacity was 32 and now you're halving it. Even if you didn't, for instance, let's say you were given both question 1 and question 2, right? A simple way to do it is your SPs per SM is getting halved. So how many thread blocks can you map? That also will get halved. So it will basically become half of what it was previously, which is 1. But try to either, if you are finding it very confusing to do it this way, in a very abstract way, try to either pictorially draw it out and then figure out, or try to have an example that's easier for you to concretely reason about, right? If, for instance, all of us have seen this example of rooms and people being put into a room and then batches, right? We see a lot of real world examples of that. Whenever you go to maybe a temple, you go to a movie theater, whenever you visit something, right? There is this notion of batches and scheduling. So if that helps you understand this better, maybe that's a good example. But hopefully this is clearer now. Any further doubts in questions 1 to 3? Okay, if not, we'll move to question 4 and see if you're able to solve it better. For the new GPU architecture in question 3, basically you have 2 SMs, 16 SPs per SM, and the same kernel launch parameters used in questions 1 and 2. How many batches of thread block to SM dispatch would be required to complete the kernel? So this is very similar to question 2. So take a couple of minutes and think about this. You should be able to answer this given that we just went through this, right? So take a couple of minutes. C, okay. Anyone else? One more answer, C. Go to question 3. Yeah, let's do that. Maybe let's cover this question and then go back to question 3. That's perfectly fine. Do you need any? Okay, you need the GPU architecture details, is it? Okay, then in that case, I'll just show that. So the architecture is 2 SMs and 16 SPs per SM. If that's what you needed, hope this helps. If you want me to explain question 3 again, please mention that in chat. Okay. Any other answers? I'll give you a little more time, then we can discuss the answer. Anyone else? Okay, if not, we'll look at the answer. So yes, it is C. So let's go back to our drawing again, right? So now you just have 2 SMs, and in question 3 we already discussed this part, that we would be able to map one block per SM. And this question also says that the launch configuration remains the same. So you would basically map two blocks at a time in one batch. But how many blocks do you have? You have 8 blocks, right? If you remember from the launch parameters, 4 into 2, 8. So you would need to do this 4 times, or you would need to do this in 4 batches. Basically, if I started indexing from 1, it would be 1, 2, 3, 4, 5, 6, 7, 8, right? So you basically have to do 4 batches of these across the 2 SMs to complete the kernel. So your answer is C. Again, this is an alternate way of calculating. Again, all of this is the same logically. It's just using different units. So we calculated in terms of blocks. The other way to do it is using threads. So at a time, you have 2 SMs and 16 SPs per SM. So you can launch a total of 32 threads. And the total work, so what you do here is, again, as we had done in I think week 3, on one side you have the total work for the kernel in terms of number of threads, and on the other side you have the hardware capability. So this is your hardware capability. Total number of threads needed for the work in the kernel is, again, you multiply all the launch parameters, you get 128. So at a time you can launch 32. How many batches do you need to launch to complete 128? Basically 128 by 32. 4 batches. So again your answer is C. So these are 2 alternate ways of solving this. Whichever feels easier and more intuitive for you, feel free to pick that, right? They're the same. There's no difference. But is this clear to everyone, or is there a doubt? Clear? Okay. Any questions? I'll just wait a few more seconds because, again, I think very few people answered this. So I want to make sure that there are no doubts. These are, again, very typical and representative of questions that you will get. So in the next set of questions, I think we'll move on to the branching and the divergence. So this is all you have on the scheduling side. So please make sure you understand questions 1 to 4. If you have any doubts, now is a good time to ask me. So if not, we'll take a 5-minute break now since we are at a logical closing point. We'll resume at 6:59. I'll leave the call running, but feel free to get a short break. Okay, let's continue. Which of the following statements is true? A CUDA thread block can execute in multiple SMs. Multiple thread blocks can execute in the same SM. Threads belonging to different CUDA thread blocks can communicate using shared memory. Threads across multiple CUDA thread blocks can be synchronized using sync threads. Take a minute to remember this. Some of these are from previous weeks. Any answers? B. Okay. B and D. Okay. B. Okay. D also. Okay. Any other answers? Okay, let's take a look at the answer. So broadly, the options cover this synchronization and shared memory apart from this week's topics, right? So let's look at all of them. So some of you said D. Why is D not correct? So this says threads across multiple CUDA thread blocks can be synchronized using sync threads. So if you remember from the previous week, we explicitly discussed that there is no guarantee on block execution order, right? CUDA makes sure that each block is executed independently, and you are, as a programmer, you do not get any guarantees on ordering, right? And particularly using sync threads, you cannot synchronize across thread blocks. You can only synchronize within a given thread block, right? So this option is incorrect. Yes, under same thread block would be true, but this says across, so therefore it's not true. Similarly, threads belonging to different thread blocks can communicate using shared memory, also false. Again, it's only within same block. Now coming back to this part, a CUDA thread block can execute in multiple SMs of an NVIDIA GPU. This is false. We again just discussed it in this week's revision, right? One block cannot be split across multiple SMs, but on the contrary, you can have multiple blocks executing on the same SM. So B is the only correct answer. So with these options, you have to pay attention to what the option is saying. Is it talking about within a particular thread block or multiple, right? Because this says multiple, it's not possible. Sync threads only allows within a single thread block. Is this clear now? Any other doubts here? Okay, if not, let's move to the next question. Consider a GPU architecture where the warp size is 16. What is the total number of warps launched during the lifetime of a kernel with the following launch configuration? Take a couple of minutes and we can then discuss. Here one answer C, one more answer C, okay. Anyone else? Okay, one more saying C. Anyone else? C, okay. This one seems to be fairly straightforward. So yes, let's go through the answer. It is C, 64. So let's see why. So the total number of threads, as you may remember from previous weeks, you get by multiplying all the parameters given here. So this comes to be 1024 for this kernel. Now the warp size that you're given is 16 and you're asked how many warps are launched throughout the lifetime of this kernel. So per warp you have 16 threads and the total number of threads is 1024. So the total number of warps that you launch for this kernel is 1024 by 16, which is 64, or option C. Any other doubts in this question? I'm guessing this is fairly straightforward. We'll move to the next one then. Consider a hypothetical GPU architecture where the warp size is 8 and a kernel program which is launched with a configuration where the total number of threads in a thread block is 32. The total number of warps launched per thread block is therefore 4. Consider the following statements in the kernel. If thread idx.x less than 16, mod 2, mod 32, mod 8. So these are 4 statements that are there in the kernel. Now you are given a few options based on these. All conditional branches are divergent for all warps. Conditional branch 4 is not divergent for warp 0. Conditional branch 2 is divergent only for warps 0 and 4. Conditional branch 1 is divergent only for warp 0 and 1. So you have to pick which is the correct option about the conditional branches in the previous slide. So I'll pause here for a few seconds and go back to the previous slide, and then you can tell me the answer in a couple of minutes. Okay, I will go back to this. If you want me to scroll to the options, you can just let me know. Yeah, the font size becomes too small. I'll try it for the next time. I think I did for this one, but some of the questions are too long and then it's not very visible. But maybe if you want this part alone, I can maybe try moving that. That should be doable. Yeah, hopefully this helps. The rest of the question is, it'll make it kind of illegible. Sure. We have one answer B. Okay. Take your time. This may involve evaluating all four options, right? So take your time. But we'll discuss it maybe in a minute more. C. Okay. Any other answers? Okay, if not, let's take a look at the answer. So I think, okay. So the answer is B. Conditional branch 4 is not divergent for warp 0. So let's again think about why that is, right? So maybe I think one of the slides is repeated. So but what you need from here is the warp size is 8. So, and your number of threads in the thread block is 32. So your total number of warps is 4. Now if you think about thread IDs in all the warps, your IDs are 0 to 7, 8 to 15, 16 to 23 and 24 to 31. Now this is all that you need to evaluate these conditions. So let's again put these conditions here. That way you don't need to remember too much. So now let's start with this correct answer and first see. So conditional branch 4, right? Thread idx dot x lesser than 8. So if you look at the warp 0's thread ID 0 to 7, all of them satisfy this. So for warp 0, this conditional branch is not divergent. This is definitely correct. Therefore, all conditional branches are divergent for all warps by definition becomes wrong, right? Because you already have one conditional branch that is not divergent for warp 0. Now let's try evaluating some of the others. Conditional branch 2. So this says mod 2, right, is divergent only for warp 0 and 4. Again, this is a simple thing, right? It's modulo 2, and you can see that all of them have even and odd numbers. So this is not going to be divergent only for warp 0 and 4, and all of them evaluate to a certain other case in warp 1 and 2. This also is wrong. And the other condition, divergence means going to else condition. Divergence, again, if you have a single if else, yes, it means that some threads are going to fall in the if part and some are going to fall in the else part. If you have nested branching, then it basically means that your threads diverge, right? So it could be that some of them go to, you know, the sub branch 1, some of them go to sub branch 3. It could be any of those cases. In a simple if else case, yes, it means that some threads are going to fall to the if part and some of them are going to evaluate the else part. So all you need to do is to come up with the thread IDs for each warp. This is again the template for all questions like this. You have to come up with the thread IDs for each warp. You have to look at these conditions, and for each warp you have to think about whether some thread IDs are going to satisfy this condition, some thread IDs are not going to satisfy this condition. That's all you need to do. So you can try this out. Again, these are very simple operations, right? Lesser than and modulus. So you can try this out, and you'll be able to see why B is the right answer. And I think we have more questions like this also, so that should also help you understand it better. Any other doubts in this question? Do you understand what the question is and how you need to solve it? Okay, give more explanation. So maybe let's take one option and go into detail into that, right? So what does the question tell you? You have warp size is 8. So going back to the definition of a warp, the number of threads in the warp is called the warp size. So you're basically told that this warp has 8 threads. So using that, we come up with the thread IDs, right? So in the warp 0, you would have thread IDs 0 to 7. And how many warps do you have? That is given by the kernel launch parameters. So here you are told that the total number of threads in a thread block is 32. So therefore, you can now figure out that you have a warp size of 8. So you will have a total number of warps for this thread block as 4. So in those 4 warps, so you basically have these 4 warps. You can come up with the thread IDs, right? 0 to 7, 8 to 15, 16 to 23 and 24 to 31. Now these thread IDs will be what the if statements use. So let's again go to option B, right? So we are talking about the condition branch 4. So let's take that 4. So it says if thread ID x dot x less than 8. This is the condition that you have. Now let's start with warp 0, right? Now is 0 less than 8? Yes. 1 less than 8? Yes. You evaluate this for all threads 0 to 7. All of them are less than 8. So all of them are going to fall under the yes or the true part of it, the if part of the condition, right? Whereas if I take warp 1, 8 to 15, and I evaluate this, then what happens? Similarly, you will have to check for warp 2 and warp 3, right? So in this case, the statement that you are given is it is not divergent for warp 0, which is true, because all the threads are going to be less than 8, and all of them are therefore going to fall in the if part of it, not the else part of it. So you can do the same thing. Similarly, you will have less than 16, right? So if you have less than 16, for instance, in warp 3, the less than 16 is not going to be true. And if you go to warp 2, you will have a 16 to 23. Again, you can evaluate whether, so what you need to evaluate is whether all the threads are going to fall in one part of it, the if part or the else part, or they are going to diverge, right? There are some threads that evaluate to the if, some threads that evaluate to the else, and there, using that, you can say whether a particular condition branch is divergent for a given warp. So in this case, for warp 0, condition branch 4 is not divergent, because all your threads in warp 0 satisfy the condition. They all fall to the if branch. So you can try evaluating this for the rest of them and see which, if any of the others come out to be true. They won't, but this is good practice for you to understand how to do this. Now, is this clearer? Okay, great. I'll just pause here for a few more seconds. People who still have a doubt, try to go through this and see if it makes sense. And then we'll move to the next question. Okay, we have a doubt. Why is D incorrect? Condition branch 1 is divergent only for warps 0 and 1. Can anyone answer that? It is not divergent for 0 and 1. Yeah. So if you evaluate this and see, so condition branch 1 less than 16, right? All of them will fall to one side for 0 and 1. Therefore, it is not divergent. So this becomes false. Yes. So I think most of you have understood this question. We'll go to the next one, but I think there are more like this. So you will understand it better by the time we solve more questions. Let's go to the next one for now. Consider the following kernel processing A, which is a 1D array of 2048 elements on a GPU architecture where the warp size is 16. The kernel is launched with a configuration of 6411 blocks of 3211 threads. Assume that each element of A is initialized to 0. So A is your input array here, and this is the kernel. And you have initializations for TID and GID. TID is simply thread ID x.x. GID is your block idx.x star block dimension.x plus thread idx.x. This is again the same definition we had in the 1D case. Now you have another variable loop bound, which is calculated as thread idx.x divided by 8. And if thread id mod 2, then you have a for loop for I equal to 0, I less than loop bound, I plus plus, a of gid plus plus. So this is the same array a that you're taking as an input, and remember that it's initially initialized to 0 and you're incrementing it till this condition basically. Now this is your kernel code. Now your question says, after the execution of the above program, what would be the value of A1035? You have 4 options, 0, 1, 2 and 4. So just note down this much and I'll scroll to the kernel. I think you'll have everything you need from there. So A1035, and these are your options. Yeah, this is the kernel. So take a couple of minutes to think about this. Okay, your options are 0, 1, 2 and 4. Any answers? We'll wait a few more seconds and then discuss the answer. Okay, we have one answer B. B was, I think, 1. Okay, any other answers? B, okay, we have one A. Okay, I think everybody is finished calculating. Let's look at the answer then. So it is B. So why is it 1? So again, we need to go back to the GID and TID part, right? So you're being asked about A1035, and you basically need this TID part here. So this comes out to be for 1035, since you have 32 threads per thread block, this comes out to be 1035 mod 32, which is 11, right? So now for this 11 you enter the for loop, and you're going to do this as much as loop bound. So what is the value of loop bound? Thread id x dot x divided by 8, which is 11 by 8, and that comes out to be 1. So you will do it, basically it's initialized to 0. You will evaluate it the first time and only then, because the value is 1. So it's I equal to 0, I less than 1, I plus plus. So it's going to happen only once, and the value of this element of A will become 1. Therefore your answer is 1, which is B. So all you need to do this is the TID value, which you will get by using this launch configuration, right? So there are 32 threads per thread block, and you are being asked about a particular element, I think 1035. So you do a mod to get the thread ID, and you need to also calculate the value of loop bound. And using that you can figure out how many times this is incremented. So depending on this value, you are going to increment it that many times. The default initialization is 0. In this case, it's only incremented once. So your answer is 1. Any doubts here? Yeah, this part. So you'll basically need to calculate the thread ID using the mod 32. So then you have a modulus condition, right? TID mod 2, that evaluates to be true, and you enter the body of the conditional statement. And then your loop bound value, again TID is 11, so 11 by 8 is 1. Therefore you increment this to 1. Yeah, I don't think warp size is very relevant here. I don't think we directly use it anywhere. Warp size is 16 equal to thread ADX dot x. Yeah, I don't think we use it anywhere. So sometimes your question will have extra information, right? Which you don't need to, but it's maybe sometimes it's given because there is a block of data that's common to multiple questions and you may need to use it in the next question. Sometimes it may happen that it's completely irrelevant and it's still given. So yeah, you can ignore it in this case. Okay, we will move to the next question if this is clear. Assume that there is a 1D input array A of n integers where each element is of the form A of I equal to I ranging from 0 to n minus 1. Consider the following kernel code snippet executing on a GPU architecture where the warp size is 8. So this is your code, tid equal to threadidx.x. If not of A of tid mod 8, B of tid plus equal to square root A of tid, else you have this block executing, B of tid plus equal to square root A tid, B tid plus equal to square root A tid. I'll come back to this. For now we'll look at the options. The above code represents a kernel suffering from divergence. During the lifetime of warp 0, what are the total number of square root instructions that are executed? Choose from the correct option below. Your options are 0, 15, 31 and 9. So the question is asking you that this kernel is divergent. For warp 0, what is the total number of square root instructions that are executed? Now I'll go back to the kernel. So these are your square root instructions, right? So they happen under certain cases. So in the if part, you'll execute only this much. In the else part, you'll execute this much. So you're already told that warp 0 has divergence, and you're being asked for the total number of square root instructions. So the warp size is 8. So you'll have 8 of these threads. You're supposed to calculate the total number of square root instructions across all threads in the 0th warp. So take your time and do that. I can scroll to the options whenever you want. Options, yes, 0, 15, 31 and 9. Okay, we have an answer, B. Okay. Anyone else? Okay, maybe this is a little difficult. Let's go through it and then see if you understand, right? So, again, the option is B, 15. How do we get that? Again, what you need from the question is warp size is 8. And here your condition is if not of A of TID mod 8. And now your A of I is initialized to I. That is what you are given, right? So in your warp 0, which is what you are asked about, so warp 0, again like the previous question, you have 0 to 7, right? These are your TIDs. Now your A of TID, because of this part, is basically initialized to the same value, right? 0 to 7. And now your condition is that value mod 8 and a not of that. So the 0 mod 8 will evaluate to 0 and the not of that will be 1, right? So for your TID equal to 0, you will get a 1 here. Whereas for all the others, you will get a 0. So that's the divergence. And the question already says that this has divergence. What you are asked is the total number of square root operations across this warp. So there are 8 threads in this warp. One of the threads evaluates to 1. So it's going to evaluate this part. The other 7 threads are going to evaluate these parts, right? So this thread will have only one square root operation. These 7 threads will have 2 square root operations. 7 into 2, right? So you have 14 here and then one more here. So your answer comes out to be 15. So this is what this is. The total number of square root instructions executed by threads in warp 0, 1 into 1 plus 7 into 2, 15. So let's again go through this quickly. So you have 8 threads and in warp 0 the thread IDs will be 0 to 7, right? And your A of TID is initialized to the same I. So you basically have values ranging from 0 to 7. What you have to do is to evaluate this if condition properly. So you will see that for 0 it will evaluate to true and for all of the others it will go to the else part, right? So if it evaluates to the if part, then you basically have only one square root instruction. If it goes to the else part, you have 2 square root instructions. So for TID 0, you will have only one square root instruction. For TID 1 to 7, which is 7 threads, you will have 2 square root instructions. So you're asked for the total number of square root instructions across all threads in warp 0. So you have to add both of these. So 14 plus 1 is 15. Now is this clear? Clear. Okay. Any doubts in this? Okay. If not, we'll move to the next question. Consider the following kernel snippet executing on a GPU architecture where the warp size is 16. Assume that the number of threads in a thread block is 32. The kernel code goes like this: TID equal to thread idx.x. If TID mod 3 equal to 0, and a nested if, right? If TID mod 2 not equal to 0, A of TID equal to A of TID star 2. This is called a multiplication operation. And then you have an else corresponding to the outer if, which says TID divided by 2. This is the division operation. Now your question says match and pair the following. Thread IDs 1, 2, 4, 5, 7, 6, 12, 3, 9, 15. Your operations are performs multiplication, performs division, does no work. And here are your 4 options. This is a lot of information, but let me see. If it's possible to maybe copy just this part, then that will maybe be helpful for you. Yeah, this is the best I can do. Hopefully it's still visible. So all you need from the previous slide is warp size is 16 and number of threads in a thread block is 32. So now here is your kernel and here are your options. Again, this will take some time, so take your time to work it out. We have one answer B. One more answer D. We have a question. How does warp size and block dimension affect current question? Without that information, will the way in which we solve the question change? Okay, let's take a look at the answer and after that we'll come back to this question. But I think people are still solving it, so let's wait a few seconds. Any other answers? Okay, we have one more answer D. Okay, let's take a look at the answer. It is D. So 1 maps to B. So thread ID is 1, 2, 4, 5, 7 performs division. So let's go back to this kernel definition that we have here. So essentially what we are doing is if it's a multiple of 3, right? You can see here the mod 3 equal to 0. The other nested if says mod 2 not equal to 0. And notice that there's no else corresponding to this, as in if it's a multiple of 3 and it's a multiple of 2, then there is nothing happening here. So that's the does no work. So that should be an obvious one. So the 6, 12 mapping to does no work, right? So that itself can help you eliminate all 3 options. But let's, for the sake of thoroughness, let's evaluate the other 2 also. So that's one fork of it. The other branch, else, which corresponds to the main thing, basically, if it's not a multiple of 3. So you basically are left with things like 1, 2, 4, 5 and 7. In that case, you'll see that there is a division operation happening here. So your division operation is basically mapped to this 1b. Again, this option has 1b. There's also one more here if you started evaluating with this. The other part is the multiplication operation, which basically, if it's a multiple of 3 but not a multiple of 2, so your 6 and 2 are eliminated out, 3, 9 and 15 remain, that would basically perform the multiplication operation. So this goes here. So the again 3a also is correct here. So D is your correct answer. So this is how you do this. So try to quickly, since it's all modulo operations, you can reason about this logically. Like I said, this is multiple of 3, not multiple of 3. This is multiple of 3, it's nested, so you have to read this as AND, right? Multiple of 3 but not multiple of 2. Multiple of 3 and multiple of 2, there is nothing. So then you will quickly be able to map these. Now there was one comment saying, does the warp size and block dimension affect these? So here the block, we are not using that in any way, right? Block I think was given as, the number of threads in a block was given as 32. The thread ID, basically you will know that because the warp size is 16, you will know that your thread ID ranges from 0 to 15, and here your options are the going to the same range, right? So again, you may not be using it very directly since you're already given certain thread IDs and you're asked what happens there. But if you're asked about certain warps, right? Let's say what happens in warp 0 versus what happens in warp 1, you will need to use both, probably both of these things, warp size as well as the threads in a block. Here we don't directly use it in any sense. So maybe just extra information. But is this question clear now? Any other doubts? Clear? Okay. Any other doubts? Okay, if not, move to the next question. Consider a GPU architecture with the following constraints. Total number of threads in a thread block is 512. Maximum number of threads in the X dimension is 256, Y dimension is 256, Z dimension is 8. Considering a 3-dimensional CUDA kernel, which of the following thread block configurations is feasible? So you have 4 options. Again, this is something like you solved in the previous lectures, right? So think about it. So you have to consider both of these things, the total number of thread constraint as well as the max number of threads in each of the dimensions. Okay, we have one answer saying D. Anyone else? Okay, D. D. Okay, I think this is straightforward. So it is D. So again, total number of threads in the thread block is 512. This is a hard constraint, right? So this product should basically come to less than 512. If you do that itself, I think it would eliminate all three of these. This would be the only feasible one. Additionally, the second level of check that you have to do is these constraints are not violated, which again I don't think it does. So D is your correct answer. So this is, I think, very similar to the previous week questions. Any doubts here? So every week I think I have at least one question which goes back to the previous week's questions also. And I put in a good mix of questions so that it covers all possible questions that you can get for your exam or assignment or things like that. So yeah, I think I have a couple of questions extra today. I think I picked the easier ones since we are kind of nearing the end of the hour. So I have one more question on divergence and one more question on launch parameters, which I will discuss in the next week. That will kind of be the spillover from this week. I had 13 questions for today, but we'll stop here so that we have another 2 minutes. And if you guys have any questions or anything that is not clear, you can mention it on chat. So I'll stay for another 2 minutes. Please ask any of your doubts or questions. If not, thank you so much for joining and interacting, and we'll continue next week. Feel free to drop off. Thank you. If you have any questions, stay back and post them. Yeah. Thank you. Thank you. Thank you.